The two-masted ship.
The good land.
Yeah.
The good land, right?
No,
Right.
No.
it's a two-masted ship.
Okay.
Oh.
Okay,
Live.
let me know.
We're live.
You're on.
Are we live? I don't see anything red on the screen. Where's the infrared? Hello, everybody. Welcome aboard, Stargazers. It is time once again for the SBAU Astro Hour. It's a 1-hour weekly vlog we do live here in Southern California in the very county that houses, oh my God, Kevin Costner. Reagan used to live here. Our spaceport is here. It's 11 to noon every Monday morning for the Santa Barbara Astronomical Unit, South Central Coast Longtime Telescope and Astrophysics Club. I'm Ronnie Heron as your host to learn a lot from these guys, very knowledgeable people I share the screen with. Introduce you to the Brain Trust here in a moment. You can watch us on YouTube, and this is number 185 we've done. We're in the middle of our 4th year of doing the Astro Hour, home of star parties and First Friday stuff, and here's what we're going to talk about this week on the program. As you hear a big truck going by, Saturn reaching opposition. Got some stunning stuff to report. First quarter moon tomorrow night. We're going for the Terminator. Terminator tells us once again, I'll be back. And there it is. Tonight, we're going to, ever thought about auroras on Mars? There's 3 of them, 3 different kinds. None of them like here on Earth. We got more on measuring long distances in space in the cosmos. Talk about the first Cepheid variable. It's in Cepheus, and we're now using spacecraft and large parallax. And we're going to check out our cluster called the Owl Cluster. Take a caravan trip through Camelopardalis. That's not to be confused with Kamala Harris running for president. And an equation for redshift. So let's meet the gang. Ladies and gentlemen, once again, having fully recovered from his trip to Europe, and I'll straighten me out on the screen here is President Jerry Wilson, 7 years. Jerry?
Good morning.
Married to the lovely Pat Forgy. And we want to auction off your dog once he gets better. No, we won't.
No.
Said he's trying to, never mind. Here's Chuck McPartland, our outreach coordinator, in front of the flag of Ukraine. He's married to our incredible merchandise manager and the new treasurer, Pat McPartland. As far as I'm concerned, they're the heart and soul of the club. Tom Whittemore's on board. He is there. Tom, retired from Westmont College, had his own lab up there, and he's married to Maureen and edits our newsletter, puts it out every week. Bruce Murdoch, married to Bonnie, who's out of the hospital and back with us, and maybe we'll see her bobbling into Fleischman next month, or maybe at the Star Party. Yeah. And doggone if Tim Crawford's not still married to Karen.
Yeah.
The man that,
Amazing.
yeah, and you're monitoring YouTube for us, and you can't get any messages?
No, I just can't. I've been having nothing but trouble with it. I updated my browser, and it's updated to nothing. It's updated.
Okay. I don't know.
Thanks again.
Yeah.
I don't know if we had this announcement, but the guy that Tom Whittemore, the guy that did the Hokey Pokey died. Is that in the news? What happened?
Oh, yeah. Well, I guess he was really heavy and fat. When they tried to put him in the casket, they had to put his right foot in and take his left foot out.
Dude, okay. And what's that other line, Mr. President? Is it what it's all about? Is it a physics phenomenon?
Yeah, I saw a bumper sticker a short while ago that said, what if the hokey pokey really is what it's all about?
Don't like to waste these things on our talk before we go on live, but we do have right now for the Astro Hour our lineup of President Jerry's forwarded silly science cartoons like this one, the Hell's Angles. There's 3 of them, 3 guys. You have the right angle, the acute angle, the right angle. They're also called the Hypotenuse Club. And watch out for these guys. They're really sharp. These just came in. We want to say congratulations. Colin, not Taylor, not our ex-treasurer, but Colin Grimshaw from Halifax, Nova Scotia, who invented the time machine. There he is seated in it. He passed away. He was born in 1947 and he died in 1438. God love him.
Well, you
Look-
can see in the back there's a cord coming out, and when he went back to 1438, he had no place to plug in.
Yeah.
He doesn't look like Rod Taylor, the guy that's starting the movie, but he looks a lot like the My Pillow Man. I'm sorry.
Uh-oh.
Okay, I have no idea what that was about. Okay, we went right by it.
Well,
We
that
do
was,
it
that
derivative.
was, it's not a cartoon, but
No.
it attracted my attention because of the two calculuses. This is the definition of differential calculus.
Mhm.
Is
But
that right?
takes some explanation.
Okay, so all of that is okay. Well, let's look at Mauridus.
It's actually a very simple
Mhm.
formula.
Well, maybe we'll go back to it. Right now, this is M.C. Escher, real name Maurits Cornelis Escher, a Dutch graphic artist who did lithographs, woodcuts, and mezzo tints. He was inspired by mathematics for all his stuff, neglected by the art world until about the time he died in 1972. Look at his legs.
Yeah.
This guy was on drugs, there's no question. And that's M.C. Escher on the beach. And here's a pie fight inside the physics lab among mathematicians inside it, throwing pie around. And here's Apollo on the moon. You know, there are two types of countries
I love
those
this.
who use the metric system and those that have been to the moon, for crying out loud.
Yeah.
So it's
They had a
240
problem because of the metric versus English.
Here's an astronaut suddenly realizing sharing his spacecraft with, oh my God, the alien. Says, so we ran the numbers. My God, it's still safer than the Boeing ship. Where's Sigourney Weaver when we need her? But look at this. And they landed the Starliner, didn't they, in the middle of the
Yeah.
night?
It landed perfectly.
Mhm.
Did they have it on screen? I think I may have left when it was coming in after the Friday night.
Yeah,
stream.
we watched.
Tom put it up on screen.
Okay, and so the two guys, the guy and the woman, could have made it back safely.
They could have, but it was risky, and NASA's
Yeah, they didn't know.
risk averse.
Here's a couple of armed
Yeah,
aliens. They just landed.
Perversity of nature.
What?
It's the perversity of nature. If they'd put astronauts on board, it wouldn't have made it back safely.
That's,
Probably
that's
right.
absolutely right.
All right, these two, this could be first contact. A couple of armed aliens land their craft right next to one of those bobbing oil wells that are turning, rotating, and they feel, I guess, that it's bowing down to them. Yeah, okay, you surrender. We get it. That's great. Now, who's in charge around here? Hello? You-hoo? Could be. Who knows? This one I've never seen before. You're going to have to enlarge
Okay,
it.
now this one is this is an older cartoon that I've seen several years ago, where a bunch of cavemen are being shown a picture of the back end of a stegosaurus, and the guy's
Oh.
explaining. Now this end is called the Thagomizer, after the late Thag Simmons.
Yes.
So then this is a comment on that cartoon that the Thagomizer is the name of the spiked tail of a stegosaur dinosaur. It didn't have an official name until the cartoonist Gary Larson did a comic about it, named it, and the scientific community just accepted it and started using the name too.
Agomizer. There's two movies you see it prominently. Can you name those two movies?
Where you
One-
see
one-
what?
You see a Thagomizer. One of them was King Kong, the original. They're in the
Yeah, and one of them was
and the other is
Jurassic Park.
what?
Jurassic Park.
I
They
don't
show
recall seeing a
Stegosaurus in there.
I do not recall seeing a Stegosaurus in Jurassic Park. They were all what's the little smaller like T-Rex is called?
The Triceratops.
Oh, yeah.
Triceratops.
No,
Well,
no,
that's one of the
Raptors.
great big
Allosaurus.
things around its
Raptor.
head.
they're named the birds are named after them
Oh,
too.
Velociraptor.
Raptor, yeah. But if you look at one portion of Disney's Fantasia, 1939, there's a cartoon version of
Of a fight, yeah.
All right, and glad you went back to that one. Thagomizer, being thagomized right now as we speak. Your poor dog was thagomized earlier
Yeah,
this morning.
my dog was bitten on the nose by a rattlesnake this
Oh
morning.
my God, Lord.
Did the snake die?
Yeah, right. No, but we were informed that the dog is going to be fine.
Really? Okay, on the
Yeah.
nose, no less, of all places. So you're
That's
not going to
kinda
use that
wonderful.
dog walker anymore, I guess.
Oh, no, he had nothing to do with it. He saved her.
So he's on a leash. Okay.
The dog was on a leash, yeah.
And it's a great retriever. I love that dog. Here we go with our concave look at the horizon up into the night
Mhm.
sky, ladies and gentlemen. Where are we here?
We are looking at, this is a finder chart for Saturn. It should be, but I don't see Saturn here right away.
Kind of in the
Right in the
middle,
There
middle.
it is, right
right
there
in the middle. Mhm.
Yeah. So the point of this is that Saturn reached opposition Saturday night, about 10 o'clock. And we're coming up, and tonight will be 2 days after opposition. And there's an effect that I'd never heard of before called the Seliger effect, where the rings appear to be enhanced in brightness on 2 days either side of the opposition. So tonight is the last night that you'll see this enhanced brightness rings of Saturn. And the reason for it is that the particles in the ring are very bright, of course, but at this time, because of the angle of the sun, they basically hide their own shadows. So it takes away a lot of darkness from the ring. And so you just get this enhanced brightness.
Where did
That's
I hear
what we're
from?
doing. It was kind of wiggly though.
Wasn't it Chuck that said the Saturn, is it going to be optima or occulted by the moon?
Yes, on the 17th. Early morning.
And will it be a full moon?
It's near full, yes, and it'll be low in the west in the morning.
So we got a couple of shows, or wait a minute, October or September?
That will be in
September.
for next week's show.
Okay,
Oh,
got it.
That'll be before it happens, and then in 2 weeks it'll be after it.
Yeah.
So it'll disappear behind the moon and stay gone how long?
About an hour.
Mhm.
Really, it's moving that fast.
Well, the moon,
The moon
and
is-
we are.
Yeah.
Yeah.
That's what I'm talking
Yeah.
about. Yeah, the moon is moving
The
that
first
fast.
occultation I ever watched visually in my 6-inch f8 reflector in 1959 was an occultation of Saturn.
Mhm.
Very impressive.
And it's cool to see the moons pop out before the rings,
Mhm.
So, sounds like you owned a Criterion, Jerry.
Actually, I ordered all the parts from Edmund Scientific
Oh,
and then
wow.
assembled it all myself.
Nice. Yeah, I had the Criterion 6-inch f8,
Okay,
but I didn't get that until about 1964, somewhere in there.
okay.
Don't have it anymore.
Now I spent the summer mowing lawns,
Me too.
doing odd jobs and helping a friend of mine deliver papers. And I spent $105 on all the parts,
Yeah.
including a mount.
Yeah, so I did the same. Indianapolis in the summertime, there's a lot of lawns to mow.
Yeah,
And it was $200, I think, shipped. The 6-inch f8.
Criterion.
Yeah.
You know when the first computers were hooked up to telescopes, laptops or otherwise, to see?
In the 70s.
Has it
Yeah.
been that long?
well, no, they had some computers, of course, have evolved quite a bit. But in the 60s, they had what's called it was a Baker Nunn camera, and it was on very high speed servo motors, and it could actually follow a meteor as it went through the air.
Mhm.
So,
But that's professional, not amateur.
yeah, definitely professional. And
Yeah, they
well,
do that for missile tracking. So they developed
Yes.
that technology in the late 40s.
Yeah.
Okay, what's going to happen to the rings here?
Oh, they're
They're
gonna
just
get
brighter.
super bright. This is a picture taken by an amateur who does very well with this. It's by Michael Carrer, taken with a Celestron 14-inch scope.
Mhm.
It was at last year's opposition.
Mhm.
Hmm.
A little overexposed.
I
Well-
think that's my computer.
Yeah. In the document, it's quite an impressive picture.
Yeah.
The Terminator.
Telescope Tuesday.
Yep.
Is that
Tomorrow.
tomorrow night, along with the
7 p.m. tomorrow night, Tuesday evening.
First quarter.
This is first quarter.
we also have a
Terminator.
workshop online, don't we?
There'll be Telescope Tuesday tomorrow night.
Mm-hmm.
I know, but isn't there also a workshop on Tuesdays?
Yeah, yeah,
So take your choice.
yeah. Well, the Telescope Tuesday, people can go out to the big box food court area where we set up telescopes. The people that come to and discuss things on the workshop generally do it on Zoom. So they're not people that can come to the Telescope Tuesday.
Never thought of a way to combine them at all?
It's not convenient, but of course,
No.
if we had to, we could.
Okay.
But this is
It'd
like
be
the perfect
helpful
phase to
laptop
show it to the
run
public.
a conversation and also run your telescope.
Yeah.
So this is the quarter moon tomorrow night. And
I think just about a half a day later, I think that you can see Rupus Recta. I don't think it's in this phase here.
No, it isn't. Yeah.
Yeah, it's
No, it's
just
about-
a little bit further, and the sword on the moon shows, which is really nice.
Yeah,
Nice.
about day 8, Tim, roughly.
Is
Okay,
Alba Tigneus in this view?
Don't know.
I see something that kind of looks like it's just
Wow.
lower than center. This is a nice picture.
Yes.
this
Is
on
this
the
Titan?
Terminator? Is this Terminator stuff?
Oh, this is just a good shot of the moon.
Okay, on any type of a face, huh?
Aristarchus. I have to look that one up.
Oh, there it is.
Aristarchus and Herodotus, upper right in the valley, the Schroeder Valley.
That's that rill there.
yeah. It was taken by an amateur with a C-14.
Are the rills the two lines at the top, or that
No,
thing
the rill
to-
is the thing that looks like a little valley there. There you are.
right next to the two craters? Got it.
Yeah.
That's a rill.
That's
huh?
a lava flow.
So it looks like there's a mound here, and then that looks like something flowed out of it and then evaporated away because it had less and less force as it left. So it probably wasn't
solidified.
lava. What's that?
Or it's solidified.
Or it's solidified. So
So you're saying lava ran down that trench?
possibly.
And you can see where it flooded a couple of craters more in the foreground. Yeah, there and to the right over there.
So this crater was a nicely defined crater before the great lava sea was molten. And then these craters here, the real distinct ones, and these are a later striking or impact. And it's possibly, in my view, I'm guessing at this, but I think that these craters here probably caused some underground. This one has got a flat bottom here. This one has no evidence of being flat. When they're flat, it's because they filled up with lava. So something that filled this up also produced some overflow here, probably from some fault under the lunar surface. And there's some minor rills over here too.
You know what confuses me about the lava when it's dried like that is there are lava fields which are filled with crumbly, crunchy, sharp pumice. How and when does it go flat and smooth?
This is from far away.
They don't ever get pumice on the moon?
There are different kinds of lava, Ron.
Right.
There's lava that flows really easily. There's lava that's chunky. There's lava that's full of gas.
Yeah.
I think in the Hawaiian language, there are like 4 or 5 different names for the different
Right.
kinds of lava. So
One of
it's
them's
not a uniform thing.
Yeah, one of them's
Yeah.
and
And there's
another one's
Hoy-Ho.
hoi.
Yeah.
Well, there's also lava tubes, right? Underground places where the astronauts can go, made by
There's lava tubes in Northern California.
Yeah.
Yeah, I
They're
had
really-
an experience there that it stuck with me. I went through the lava tubes, and I had an old Coleman lantern that actually ran on white gas. And as I went into the lava tube, the lantern started getting dimmer and dimmer. And dimmer. And I said, wait a minute, that's too little oxygen. So I turned around and came back out.
Wow.
Ooh. Well, one would think that a volcano is just full of lava tubes, wouldn't it?
They probably are. And there's
Are they?
probably a lot of lava tubes on the moon that are open to the surface. They've been photographed from orbit, where the temperature is moderate inside and would shield any astronauts up there from radiation.
But does science know that there's still lava underneath? Is there a magma underneath the moon's surface?
Yes,
There is. It's still liquid.
that's what
There's
they're
There's a
saying.
small amount, yes.
Okay, we're now switching to Mars.
Ooh. 3 different types, right? Auroras are us.
Excuse me a second.
Got to sneeze?
No. Hello?
Hi, Jerry. It's Krista at Dr. Brennan's office.
Yes.
Hi, I'm calling to confirm that we'll see you tomorrow at 2:15 for your
Yeah.
3-month recheck. Okay.
Yes. Okay, thank you.
Thank you.
Bye.
Bye.
I had to answer that because I thought it might be about my dog,
Oh,
but it's not. It's about me.
Just
but
you.
you notice how those people that call you up can't be terse. They've got to go blah, 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 blah,
Oh, she was pretty terse.
Well, she could have said the same thing with half the number of words.
Yeah. Okay.
Right.
Okay, back to this. This is about auroras that special types of auroras that occur on Mars. These are pictures of auroras on Mars. And everybody's familiar with the auroras we have on Earth, but Earth has a fairly strong magnetic field, about 1 Gauss. And so the particles, the protons from the solar wind, go up, and the magnetic field shields most of the Earth, but it's a dipole field, so the protons can travel around and come in at both poles, the North Pole and South Pole of the Earth, and so you get impact with the protons and the Earth's atmosphere, and that generates light. There is no strong magnetic field on Mars like that, but there are weak magnetic fields. And the protons still come from the sun, and they come streaming into Mars, but they're not redirected to the poles. So you get different kinds of auroras all over the surface. This one here is a local aurora where there is a weak magnetic field that is due to magnetic field generated or magnetized material in the surface of Mars. And it does some directal streaming, but it's not as intense as it is on Earth. This one is general impact over the whole surface.
So when you say protons, these are like naked hydrogen centers on their looking for electrons?
Yes, that's right. They're ionized hydrogen atoms.
That's mostly what comes out of the sun. The electrons, where do they go?
Oh, there's electrons too, but they're so energetic they don't hang around. They can't shake hands and hold hands.
Oh, they're not connected.
Yeah.
Well, it's so hot that the hydrogen is just a soup. The electrons and the protons aren't necessarily connected with each other.
So it's only hydrogen if the electrons are orbiting one electron orbiting one proton, right?
It's still
no, you can have a hydrogen. You can have oh, come on, what is it called? I can't remember. The word escapes me, but ionization. It gets ionized.
Yeah.
Which means that the electrons get stripped off of the proton, so it's a naked proton.
Wow. No neutrons are in there?
The sun is full of, we talk about the fusion of hydrogen into helium in the sun, but it's not the whole atom that it's involved. It's only the nucleus that's involved. There are no atoms in the sun because it's too hot. It's all ionized. Once they're ejected from the sun, then they start losing their energy and they can start forming hydrogen atoms, but there's still a lot of protons around there. And so
About-
it's primarily proton bombardment on the moon and on Mars.
How
And
about neutrons?
there are neutrons, but they don't produce the same effects that charged particles do.
Well, deuterium has a neutron in it, does it not?
Yeah, it's heavy hydrogen.
Right.
Well, did I hear once that neutrons are nothing more than a proton merged with an electron?
Plus a beta particle, or what is it? A
Neutrino.
Yeah.
A neutrino, and that's what makes it
A neutron by itself in free space has a half-life of about 15 minutes. It's not a stable particle unless it's in a nucleus.
What happens to it?
It decays into a proton and an electron and a neutrino.
Well, then it becomes a hydrogen atom, wouldn't it?
No, it was a hydrogen atom. Oh, yeah. Or it doesn't matter. That's the electron going around in the orbit.
Yeah. If
It's hot enough
if
that-
you have a neutron and a proton bound together, that would be a deuterium atom or a deuterium nucleus, and it's stable.
And that's the
So-
ionized, right?
No,
That's not the ionized?
It's
What-
it
what-
can be
that's just the
ionized or
core
not
of the
ionized.
atom. You also have tritium, which has two neutrons and a proton.
Yeah.
you don't tend to
Wow.
find that in the sun, though.
No.
No. So anyway, this one, the diffuse aurora that happens over a surface is produced when there's some intense event on the sun, like a coronal mass ejection. And the part of Mars that's facing the sun when it hits, which it takes some time for the mass ejection to get to Mars, but when it does, then you get this thing. These are actual photos of different auroras on Mars.
Well, I'm sure it wasn't laid out in square pieces of patches, was it?
Well, that's the scanning of the satellite that went around it. It doesn't get it is not a wide angle lens. It doesn't see all of Mars. It sees a
And-
little bit of it, and they have multiple passes, and then they paste them together.
Yeah, that's a mosaic picture, Ron. That's not at the same instant.
Yeah,
I didn't
each
think
one of
so.
these are a snapshot.
And the color is right, violet?
All these things that you see are all false color.
Oh, so it may not be that color, right?
Yeah,
But hydrogen does glow in a pinkish red.
the hydrogen alpha line is at 620 nanometers or something. So
But
It's
this
very-
isn't necessarily fluorescing hydrogen.
no,
Well,
It's carbon
in the-
dioxide atmosphere.
Yeah, I was going to bring that up too.
In the first photograph on the left, are the poles left out for some reason?
the magnetic fields on Mars do not focus on the poles like they do on Earth.
Really?
The only field that it has is local magnetic materials in the surface that produce weak local magnetic fields. And the aurora line up with those fields.
It's similar, Ron, to the way we can tell what the past magnetic field of the Earth was like, because if you have molten rocks that respond to magnetism at the time the field goes through them, and then they freeze out, they retain the magnetic field.
Orientation, yeah.
Well, are there any pictures of these taken from the ground, from rovers, or is it all done from space?
Now,
There
these
is a picture of an aurora from rovers, but here these are from spacecraft
Yeah.
orbiting.
And there's three kinds, and those three don't exist on Earth, I understand.
No, some of
They're
them are
not
similar.
dominant on Earth.
Oh,
The magnetic field on compared to Mars, the Earth's magnetic field is dominant, is much stronger. And so all the aurora effects we see come from that. It sort of erases these.
It's more like the left-hand picture, but globally instead of just in local spots like that. And whereas it can be global, it's more likely to be around the poles because that's where the protons get channeled.
you suppose the ancient Eskimos on our planet thought they were gods talking to them, or?
Actually, they thought that was, departed spirits and stuff.
I'll bet. Wow.
Then when you die, you go out through the western gate.
Well, that's here. Yeah.
The Indians thought that.
Okay. This looks like the sky, not Mars.
No, this is our sky. And this is showing where Cepheus is. Let's see if I can find it in here.
It's
There it
reverse
is.
text right there. Yeah.
Yeah. So this is the centerfold. I find these very useful when I'm out in the field, holding it up to get oriented. The great square of Pegasus. And my planetarium software doesn't produce as nice an image as this. It's all cluttered. But the constellation of Cepheus is right there. And down around this region is Delta Cepheus. And Delta Cepheus is the first. This is Delta. So it is Alderanum and Delta Cephi. This is the first Cepheus variable. And it started the candle, the range of candles for distance measurement. It was understood how this could be used to get distance measurements for collections of stars. It was the thing that Edwin Hubble noticed in the Andromeda galaxy, a Cepheid variable. And he was able to, from the apparent brightness of the Cepheid in the Andromeda galaxy, and the knowledge that it had a certain inherent luminosity, using the inverse square law, he derived the distance and proved that we were not the only galaxy in the universe. The other, as they called them, spiral nebulae, were actually galaxies outside of our own. And over here is M31, the Andromeda galaxy, a constellation away.
Forgive me for forgetting what Cepheus is. What kind of animal? Is it a whale?
It's
King.
the king, the husband of Cassiopeia.
Yeah,
Oh,
it looks sort of gender
Exactly.
neutral. I can understand your confusion.
whale is simian. That's what the word simian means, I think.
No,
No,
Is it? What
Simian
is the
means
whale?
an ape.
Satus.
Oh,
Cetus.
there's no
Cetus.
whale up there, is there? Is there a whale?
yes,
Yeah,
yes.
Yes,
Cetus.
not here.
Not
Okay,
shown here.
the king. I got it. Interesting.
Okay.
And-
Now, getting into distance, this is a sad story.
Yeah.
This is a sculpture of an astronomer symbolically measuring parallax to measure distance. It's made from parts of the Yale Columbia refracting telescope built in 1924 and destroyed in 2003 by a Canberra brush fire,
Yeah.
which burned out and destroyed the Mount Stromlo Observatory.
Wow.
What is that dinging sound?
So they didn't clear the brush around it.
I guess they didn't do something right. But it's a neat statue, and it starts our discussion of how to measure distance to things.
Mhm.
The best way to do it, the most positive way and the first way, was by parallax. And this is schematically shows that process. This is the Big Dipper, and there's a star in the Dipper. And as the Earth, but the red star is much closer than the stars of the Dipper. So as we go around in our orbit, we don't have two Earths, but this is the Earth at one position, and this is the Earth 6 months later. And so it has moved over, and it makes it look like this star has changed its position. By
Right.
measuring that motion, we can figure out, we know this baseline, we know the angle, we can figure out the distance to the star. And we've done that, the search for a parallax. It was understood that stars have to do this, but it wasn't seen. The effect is so small that telescopes weren't capable of measuring that until they got up to about 10 or 20 inches in diameter. And then they could start seeing these very slight shifts in
I think it was a 9-inch scope they first measured it in, but it was in like 1838.
the Great Dorpart refractor.
Yeah. I mean, Galileo knew that this should happen. And so he was a little confused that he wasn't seeing it, but he just didn't realize how big the, space was.
Yes. Yeah.
I think it was
People would-
Bessel
there's a
that
book-
did the measurement.
Yeah.
There's a book called Parallax that
Yeah.
describes the search for that known effect down through history. This represents the central bar of our barred spiral galaxy, the Milky Way. This represents the effective distance from the Earth, from the sun, that we can measure parallax with earthbound instruments. And this is the extension we get with, for example, the Hubble telescope has extended direct measurement of parallax by a factor of 10, where we can get almost to the core of the galaxy, 30 light years away.
30,000.
30,000, excuse me. I was struggling in my brain between parsecs and light years and left the 1,000 off. Yeah, so anyway,
The Hubble adds, it's not that much distance between our earthbound scopes and the one in space, is there? How would it add much?
Atmosphere.
Yeah,
What?
it gets a much higher resolution.
Oh, is that what it is?
Because
Okay.
the atmosphere doesn't wiggle when you're out in space. So this represents our, oh yes, there's one other thing too, going back. You can get a longer baseline than the Earth's orbit. Go back one more. You can get a longer baseline than the Earth's orbit because the sun is traveling through space. And so instead of taking a picture 6 months later, say 30 years later, you've moved way bigger distance than that. And so you can see closer stars move over that period of time. But added to the parallax is also the star's proper motion. So you have to determine that and take it out. But in principle, and that technique is not as well used because of that complication with proper motion. Proper motion is sometimes difficult to separate from parallax.
But the red star they're doing parallax on in this photograph, this diagram, is closer than those 7 in the Ursa?
Yes.
And that's just a notional diagram. That's not saying it was
Right.
done with a star near the Big Dipper,
Right. You can
No,
get parallax with your own eye by sticking your finger up and looking at what out of one eye. See what's behind in your room, see what's behind your finger, and then look through the other eye and you'll see that the finger's in front of something else in your wall. And that's basically parallax.
Jerry, a question for you. Is there a simple way of explaining measuring proper motion?
I wasn't prepared to do that.
Well, let's maybe
Tim, that's just where you look at the position of a star and a couple of years later you look again and you see that it's moved.
Yeah.
Like Barnard's star.
Okay.
So you also have to take, it has radial proper motion and lateral. Proper motion is the lateral, but you can get the component of it spectrally, whether, whether it's traveling toward you or away from it.
Okay.
So you use spectrometry and the parallax. But that's a good question. We ought to cover that another time.
Well, you should be able to tell its distance too from its brightness change.
Excuse me?
The distance doesn't change that much.
Okay.
Yeah.
How would you know that it's moving versus the parallax makes it move? How do you know which is which?
That's because you have to do something to figure out what the proper motion is.
Yeah.
You can do it by association if it's with another cluster of stars.
And Ron, parallax makes a star appear to move back and forth, whereas proper motion is continued in one direction.
Okay.
But if you do that where you depend on the sun moving a long distance, there's no fourth. It's just all one direction, and that's when it gets complicated.
Wow.
This is our sun. This is our Milky Way. It's lost its central bar here, but that's just a graphic error. This shows the original parallax difference. There's Earth. And this is the distance
Yeah.
to the scale of the galaxy, the new parallax limit with using our satellites, particularly the Hubble, but James Webb does it too. And that is from 0 to 10 here to 10K. This is 10,000 to 100 million light years, getting out to this distance. And then galaxies hosting Cepheids and type 1a supernova is the thing used for this range of galaxies, which is nearby. And then after that, 100 million to 1 billion light years out, that's where we look at redshifts for distant galaxies and try to use the redshift as a index or the standard candle for distance to those things. And also the type 1a supernova are out in this very far thing.
Mm-hmm.
The type 1a has a standard brightness that it can go to, and it has a very characteristic light curve. And you see that light curve, you know you've got a luminosity calibration. Questions?
Well, between infrared and radio, they're pretty close, aren't they? Isn't that what
This would
The
be
next-
ultraviolet, and this would be radio,
infrared? And then
infrared.
below that, to the left of that would be radio waves.
That's correct.
Okay, at what point do you shift from what lenses or whatever you call that concave thing on the web?
Just use different detectors.
Well, you
to a
also have
radio-
different mechanisms.
Okay,
Could be
but
a mirror, it can be a lens, it can be a germanium lens if they're going to look into the infrared.
Use
when-
different detectors, Ron, and then you have to change your reflecting surface as the wavelength changes.
But what are we looking at with radio telescopes, the big, huge dishes, when we're only looking inside the,
You're looking at
Filtered
radio
away.
emissions.
so things are not just sending light waves that are either ultraviolet or infrared or clear over the spectrum, but they're sending radio waves?
Radio waves are light waves.
Well, I know that, but I thought they had to be broadcast or
Well,
transmitted somehow.
they have to be emitted, and natural processes do emit radio waves.
Yeah, you're emitting microwave right now, Ron.
Can you see it?
Yeah.
Oh,
Okay.
yeah.
Look at the microwave background.
Glowing like a light bulb, Bub.
Well, I'm gonna see.
Yeah.
I'll check with Jerry's doctor tomorrow.
Well, when we were at the
Tim,
at Refugio, there was a guy there with an image intensifier thing, which was really neat. But that's looking at infrared, and then it converts it into an electron image, which gets onto a phosphor, and then you can see it.
Yeah, that intensifier is it's a cascade device.
Right.
Well, this wasn't an image intensifier, Jerry.
Oh.
This was actually an infrared monocle.
Okay. Never mind.
binocular.
You know,
We had a guy in
I
the
would-
club, Jerry Polivka, who made kits where you could make your own radio telescope, and I've
Yeah.
got one of those. And it can detect the sun, it can detect the moon, and it can detect satellites that are broadcasting.
Yeah, Jupiter's a good emitter of radio waves.
But it also can detect trees and people. And so when we would bring it sometimes to school science nights that were actually, the sun hadn't set, the kids loved pointing it at each other because you could see their microwave radiation.
Yeah.
But whereas the light waves require relatively small pickup things, a meter across, how big is the web? It's 18 meters, and yet the radio
8 meters.
requires a football field, doesn't it?
Yes, you have to change your reflector based on the wavelength.
Yeah.
Okay, so we don't have any radio telescopes out in space?
There are some, but they're small.
Really?
We talk back and forth with our satellites using radio waves, and so they have antennas. Antennas are the equivalent of a lens in visible light It's an antenna in radio waves.
But it's a dish, right?
It can
It's a
be.
bowl.
It can be a dipole. It can be all sorts of things.
Is it shaped exactly like a concave lens is shaped?
Some of them.
Some of them, in other
But
words,
the thing about, I think China has the biggest concave thing. It replaced Arecibo when Arecibo collapsed.
Yeah.
But the
And
Chinese
it's a
one is
spherical.
bigger. Yeah. They're spherical, and so they don't produce a point image. They produce a line image pointing up, straight up inside, called a, what is it called? A caustic curve. That's why they have that big antenna hanging down inside to pick up all the radiation that focuses.
Jerry, can I make a comment just off the side here? Is that you're talking
Please
about
do.
when we were talking about the supernova, the Type 1A, at outreaches, I used to tell people, they're kind of a standard candle. And by that, if you saw like a car light up in the mountains, it appears very faint. But if you saw a car light coming down the street, it's much brighter. But they're both headlights.
Yeah.
And so in a way that supernova, the Type 1A does that, correct?
Yes.
And that's different from the Cepheid variables.
Oh, yes.
Yeah.
Okay.
And Ron, actually, Tim, we've since figured out that there are might be two kinds of 1A supernovas. So there's 1A, 1B, 1 whatever. We used to think there was only one kind.
Okay.
But there's a couple, and they're both, at least the ones that are used for the distance ladder, are related to having white dwarf stars that accrete beyond a certain limit and then detonate. But you can have that happen two ways. One way is they're orbiting another star and sucking material off, but the other way is a pair of white dwarfs in an orbit that spiral in and collide with each other. And so that was one of the things they had to work out to get the distance ladder more accurate.
But I'm kind of correct at the outreaches by saying these are kind of
absolutely
candles.
Yes.
Okay, good.
Okay.
On the issue of the antennas that they use, they can be very large. Out in the desert on the way to Mammoth on Highway 395 I've forgotten the name of it. Art Harris and I visited there, where they have a 130 meter big radio telescope, but they also got one that's covers several acres, and they're individual antennas that are broadband, and they all are cabled back to the central thing where they do the beamforming, and they can get some very good pictures with that apparatus.
Mm-hmm.
Yeah, there are very large arrays out there in the Owens Valley, and then there are very large arrays in Argentina also that do.
Okay, so that's right. It's Owens Valley Radio Observatory, ORNO.
Yeah.
That's right. Yeah. Now this particular graphic shows the extragalactic distance ladder. This is the farthest stuff away. It starts locally, 1 kiloparsec, globular cluster statistics. Our Lyra stars. This is it does a similar thing to Cepheid variables.
Oh.
And the Cepheid variables are here too. But these contribute, they couple together into these chains of light candles or distance measures, and they all feed into the Hubble constant. They all can measure redshift or look at redshift way back and see and come up with a distance to them. That these distances are all slightly different that they come to, and that's what we covered last week as the Hubble tension. So it's where the different technique you use to measure it comes down very precisely to things that don't come to the same answer. It's one of the great unsolved mysteries of our current time.
But we're getting closer to an answer, because one of the things we did talk about is they're finding that with using some of these other measurements that aren't as sensitive to things like dust between us and the distant galaxy, like this RGB tip measurement that you see off on the left, a bunch of the measurements converge toward a value that's within the error bars of the others, whereas the supernova 1As are more divergent. And so it looks like there's a systematic error somewhere in the supernova definite determinations.
Now, this is the one that we I'm more familiar with. You start off with Cepheid variables. You look at large Magellanic Cloud Cepheids. local group and Hubble Space Telescope CFIDs. And then you go to the next step beyond that is the supernova type 1A. And that gets you a certain distance or a certain Hubble constant up here. I won't go through the details of all these because I keep forgetting what they are.
Do you know what PNLF is in the middle?
No, I forgot.
Okay. This is
I think it's planetary nebulae, something, with how they disperse.
Yeah, especially since it's got a supernova 1987A light echo, and that is going off with the planetary nebula. As the supernova light hits clouds of previously thrown out material, then that light comes to the Earth later, and we see an expanded view of things getting illuminated. It gives us a good distance measure.
what those blobs that are being seen and recorded by the web, are they on the edge of what they think is the visible universe, or are they
They're
just
way up. They're way up. The stuff on the edge is in these measurement techniques up here. Those were 100 megaparsecs beyond a gigaparsecs up here. This is the getting back to the very early universe. Okay, now this is the Hubble's data, and you see it goes out to 6.52 million light years. And here is today's measurements. The entire chart you just looked at is this little square down here.
Oh,
And then as we get up farther and farther away, the Hubble constant may need to be redefined as the Hubble variable.
Hubble parameters, I think what they
Hubble
like to call it.
parameter, yeah.
Yeah.
and what does that mean?
It means it's not a constant
Yeah,
because of the accelerated rate of expansion.
yeah.
Oh,
Things are different in the far away and that therefore very early universe than they are today.
so it goes to an asymptote there at the end?
That curve suggests that it goes asymptotic, yes.
Huh.
so Tom Whittemore's ball of dough with all those raisins inside, the raisins in the middle that are close to each other aren't moving as far apart or as fast as the ones out on the edge of
Yes.
the brim, right?
Yeah.
That's
effect,
as
yes.
viewed. That's as viewed from the center raisin. But if
Yeah,
you're
and
viewing from an edge raisin, the center seems to be moving far away.
yeah, and the edge raisins are the first ones to taste.
Yeah.
Yeah.
and Tim, that
What the-
asymptote
Yes.
would be the age of the universe.
Okay. Okay. That's what I was thinking. It seems to stop there and it goes back right to the Big Bang.
Yeah.
If there was a Big Bang.
If there was a Big Bang. Okay.
Right.
So
Yeah,
it's
up to about,
13.6, so-
Jerry, I think we're out to about 14, Z14, somewhere in there.
In
20.
observation, yes.
Yeah.
Wow. Hmm.
Okay.
Hang on, gentlemen.
Now this is for just for reference. This is Z, which is a measure of the redshift,
Mhm.
and it is the ratio of the redshift of the velocity outward to C, the fraction of C it is 1 plus that over 1 minus that, and the square root minus 1.
Right.
Is
So that's
the observed-
recessional velocity, Jerry. Recessional velocity. Yeah.
Okay,
Mhm.
now to an easier topic.
Yeah.
I was just going to say you could take that equation and run some math on it, and you can get the recessional velocity if you measure the Z.
Yeah,
Okay.
You're telling us your students used to do that at Westmont?
Sure do.
yeah.
I did it
Really?
just the other
The-
week when Jerry touched on this subject. It was a couple of Mondays ago. And I remember just calculating how fast things were moving away for Z is 14. And they're booking. They're moving fast.
Yeah, these are what we're discussing is junior level introductory relativity.
Yeah.
General relativity. Now this is the owl cluster. There's the two eyes of the owl.
Mhm.
And if you spin, it kind of reminds you of the face of an owl body down
There's the
here.
little wings. Yeah.
Yeah,
4, 5, 7.
it's a beautiful star cluster.
Right.
One of Tessa's favorites.
One of Tim's.
Yeah.
Tim and me, Ken.
I got Tessa into this, and then every time I went to it, she goes, "You're stealing my thunder."
Yeah.
Well, this is an amateur picture taken by a well-known amateur, Bob Farah. He has presented a lot of stuff at the advanced imaging conferences up in San Jose, which they no longer hold now. It got too expensive to rent the San Jose Convention Center.
I see.
So they now operate a library of past presentations.
Okay.
Is he the one that named it?
No.
No,
Who named it? Some guy from one of the magazines, right?
Dave Eicher from Astronomy
Astronomy?
magazine christened it the Owl Cluster more than 40 years ago.
Okay.
What did they call it before then?
I don't know.
NGC 457.
NGC 457.
It's interesting at the star parties this last Saturday. I was looking at M22, and the guy says, "Is it known by another name?" And I went, "Well, I don't think so."
Yeah.
But it's in the teapot.
Don't know your telephone numbers in the sky yet, huh?
Yeah.
So at 11 o'clock in the evenings tonight, tomorrow night, but it'll look the same tonight. This is the finder chart for Camelopardalis. It has a big lot line here, goes way out there for a camel, but it has very little development on it yet. So
Well, that's the neck of the giraffe going way over there.
yeah, for some reason they don't give it any red lines.
And so this
But
is
it's
Kimball's
got-
Cascade.
Right.
Yeah.
That's where we're going.
You can actually kind of see it there.
Yeah.
This is a list. Lee
You see
Johnson, I think.
1501, Tim. 1501. They have the splash.
1502, isn't it? I thought.
1502. Yeah. One of them's planetary, and then one's an open.
Oh, okay. Okay.
So 1502 is the open, 1501 is the planetary.
Yeah. Seen them both.
Yeah,
They're pretty
open
cool.
cluster planetary.
It's the splash in the creek,
That's
Yeah.
it.
and
That's it.
splash in the pond, I guess.
Yeah.
Oh yeah, so it's Lee Johnson put together decades ago this list of interesting objects in Camelopardalis for visual observation. Among them, and this is the objects on the list where they're located. And Kemble's Cascade is this line of stars, roughly linear, that ends in this star cluster down here, 1502. Which, as you can tell from the chatter from the group, that everybody's familiar with this.
Yep.
Yeah, it's really pretty. It's binocular object.
Binocular object only, really.
Oh,
I found the photograph that I took of they call it the long wave array out there in Owens Valley.
Okay,
And it's just a whole bunch of conical antennas that are spread out over a big field.
yeah. Yeah, it's very impressive. They used to give tours out there too, if you call ahead.
We took it. We went. Art Harris and I went out there. Spent
Okay.
all day there.
I was going to mention, there's also a beautiful collection of radioscopes up at Bernie Falls, up in that area. And
Really?
one summer I got a tour of that by a graduate student. Okay.
I always tell people that Kemble's Cascade, not only a binocular object, but it kind of looks like a slow motion of a pebble dropping into a pond.
Yeah.
And
no,
at the bottom, that 1501, 1502 looks like the splash.
1502, yeah. Mhm.
Okay,
well, if most stars out there are either binaries or trinaries or quadraries or whatever, at what point does it become a star cluster?
When they're loosely gravitationally bound and not orbiting each other
Right.
in a really obvious
They don't
way.
crash into each other.
first you see an association, a visual association that could be a cluster or an asterism.
Huh, what is that?
And then you measure the distance to these things, and if they're all at the same distance, then it's probably a cluster.
But there's not a minimum for a cluster. You could have a cluster of 5 or 6.
I don't know about that.
Yeah,
I think
don't-
they're
that's
just called
splitting
sparse
hairs.
clusters.
Okay.
It's like you see a double star. Is it a binary or is it just a double?
I don't understand this 1 through 8 arc. I don't.
That's an arc of stars that you can
Yeah.
see in 1502.
Oh, okay, okay.
Yeah,
Is it an asterism?
Yeah.
that is an
Uh-huh,
asterism.
Okay. Without a name, just
It's your
8 numbers.
beret, Ron, it's your beret.
Oh, my.
Yeah, but you have to measure the distance. They used to think that Alberio was a double star. And then I found that the two stars that you see are about 300 light years apart.
Well, that is a double star, but
Not
they
a
thought it
binary.
might have been binary.
Okay, but it's not a binary.
Yeah,
It's two
Well, we
stars.
still don't know that for sure, but it goes back and forth.
Well, the last time I was reading, they did precision measurements on its distance, and they were about 300 light years apart.
Yeah, they're still going back and forth on that.
Okay.
Oh, how big of a scope do you need to see this one?
Yeah.
18.
Wow,
I've seen an 18. Yeah,
really? Wow.
You've probably seen a 10, Tim. Good night, you know.
Well, I could try it, but man,
Not a donut, but maybe it's a bagel.
yeah.
Looks more like a tic tac.
Okay, gentlemen, learning a lot. You want to end up with this, Jerry?
Yeah.
Wow.
What are we looking at again?
this is NG or the IC 342.
Wow.
Oh, okay, I knew that.
Yeah, it's just
And
a pretty.
you took the picture? Who the hell
No,
took this
No,
picture?
I didn't take this picture.
Oh, okay. Can we see this on the next Saturday night at
These
Star Party?
pictures are from an article in Sky and Telescope.
Hmm.
Got
The current issue of it. It just has some dramatically good pictures in it.
Yeah, this is pretty faint.
Yeah,
Well, that's definitely a galaxy in the middle. Gentlemen, have we run out of time? Shall we plug some stuff real quick? Between now and Saturday night Star Party, we got 2 events tomorrow, one online, the other out at Camino Real. And who's
Yep.
going to be out there?
Telescope Tuesday at Camino Real Marketplace. Pat and I'll be there. Edgar usually comes, and David Larson.
Okay.
And then on Thursday we have Carpinteria State Beach.
Aha.
And then Saturday is the museum monthly public observation.
Bring
That'll-
moontan lotion.
what's the weather outlook for Saturday?
Cooler.
It's looking decent.
Yeah, it's going to be cooler.
15-mile-an-hour gusts.
Bring some moontan lotion.
We'll be hidden in the buildings. The gusts won't bother us.
Well, that's the meeting part, but the telescope part, you'll be exposed.
No, I mean between the buildings.
Yeah.
Watch out for
Okay.
the rattlesnakes, especially if you have a dog. And our
Yeah, I
next
gotta go
speaker-
down to the hospital and see my dog.
Yeah.
Okay, I hope he's okay. Next month, a UCSB undergrad talks to us about dark matter. I'm wondering what the pictures on the screen are going to look like. And hope,
Did they give your dog a shot of antivenom?
I haven't heard that yet. They said they're going to evaluate the dog and decide whether they need antivenom and how much.
was
And
it Ronnie?
Ronnie, is that meeting the guy's just going to load one slide?
Yeah.
I don't know. He's a young guy from UCSB. There's a big program looking into dark matter out there at the university. He's going to give us the latest. I can't get him to reply back right now. He may still be on holiday. But we'll hopefully have the museum's planetarium open. I'd love to hear.
That's gonna be good.
Well, it's opening on the 18th.
Do we have anybody to run the show?
Well, it's opening on the 18th.
I
So
think, or the assistant, Ilya.
Isla.
I can do it.
She's the one that runs the scope.
So can
Well,
Tom Totten.
That's the
Oh,
scope.
I do
In the
too.
planetarium,
Oh, the planetarium.
I
yeah.
don't know. I could run it. Tom could run it.
Yeah.
We got a bunch of
Okay.
people that could run it.
So you
Yeah.
think
I
we'll
could
have
prune
a,
it.
because we've been convening at 7 o'clock on first Fridays and just commiserating for half an hour before the show starts. This time we'll get to go get a plush seat inside the IMAX.
Yeah.
Yeah.
We actually, the planning meeting decided we were going to start the meeting at 7, and then everybody started coming at 7:30. So
Yeah.
Well, we'll see. We forgot to tell them about possibility of planetarium last Friday night. Nevertheless, gentlemen, we thank you. And as our beloved outreach coordinator would say, Hasta Nebula,
That's the
everybody.
nebula.
Bye, everybody.
Thanks.